could be the batch size over here. Rather than, so this is really what I was calling, if you don't take into account x and b, the w and b is our theta essentially. So our cost function is j of theta. And if you take, the reason the author has a lot of summations over here is basically this is the number of layers, then the outputs and the inputs, right? So basically all the weights. So essentially this means is weights in all layers, not just one. Okay, so this is our extra regularization term. And of course, if we take the derivative, 2 cancels, just the wij is left. Once we are taking the derivative with respect to w to compute the gradient. And so as we update this, so remember we will be doing w equal to w minus, learning rate times the gradient of w, right? Okay, so now as I said in this part over here, there will not only be the regular gradient plus what else? Plus lambda w. Because the derivative of this, as you can see, will be lambda w. So that's what I mean. If once we do partial j over partial w, this will become lambda w, right? So once we go to this part, this will be whatever gradient we computed for this term, plus lambda w. So that's what I put in the code, plus lambda w, and there's a minus sign over here, so essentially the minus sign appears over there. So this becomes minus, right, because of this mark. And the whole thing gets multiplied by the learning rate. See, learning rate, right? Okay, so now let me quickly show you the code.
Question. If the weight is negative, could that actually cause it to increase?
No, because it's in the cost function, it's the square term, right? So even if it's a negative, it's contributing positive value to the cost function. And so if this is our j of theta, as we keep updating the w, right, each time w equal to w minus learning rate times the gradient, essentially we are reducing the cost. So whether a negative w or positive w doesn't matter. Whatever the value is, if it reduces our j of theta, that's a better w.
So it's not the derivative of that, right? Because then it would just be w. It's actually w squared. So as you were saying, it's always positive.
Correct.
Okay, got it.
Okay, so anyway, in this particular article, the author covers one more regularization technique. Okay, but in my opinion, we can skip that because in the early days, meaning if you go back 5-7 years ago, that would have been useful. Now there's a very, very simple technique which is called dropout. So let me cover dropout, then I'll give you a short break. But before I cover dropout, so does this make sense again? So take a look as we are upgrading w equal to w minus learning rate into 1 over the batch size into whatever gradients we have created, computed I mean, right? So this is the normal update, nothing special over here. What's once again the extra term got added over here? Minus the, and why did we add this? Because of that lambda w square in the cost function. Okay, so anyway, this may not give you better results on our existing data, but like I said, as we play with more complex models, you'll definitely see improvement if we add this regularization.
Oh, Professor, sorry, but why is it minus the lambda? Why minus is there? Why not plus?
Why not plus? Okay. So once again, if you take a look at our j of theta, right? Over here was our regular whatever yi minus ai square, right? Then we added this extra term over here,
Lambda.
0.5 lambda w square. Okay. So now if we do go partial j over partial w, okay. So we'll have, suppose whatever we come up to that w, because remember this will be a chain up to that w. Suppose I call this grad w. Or what did I call it over here? Grad w.
Layer of lambda. No,
Yeah, w grad. Suppose I call this term w grad. Okay, then what will be the derivative with respect to w?
2 times 0.5, so cancel. Lambda w simply.
Lambda w, right? Okay, so that means each w will be updated how? W minus the learning rate times the gradient. This is, which is w grad plus
Oh, so that's why it is.
lambda w, right? But in the code, I separated
Separated
this out and I separated this out. So that's why you got two minuses, a minus and a minus. So if I expand this, you will see two minus.
Yeah, got it. Thank you.
Here allow the W to decrease the overall W's to reduce the overfitting. It's like
Correct.
cancel the zeros. But what confuses me here, the W is all the W's like Wij.
Correct. So effectively, it will see. Let me emphasize one part. Okay. As we start using more of these TensorFlow type libraries, right? What you will notice is creating the network is extremely easy. Okay, but it's the cost function that we will create in a clever way. My goal is for you to be able to learn how do we create these cost functions so that we can control what kind of network optimization it will result in, right? Okay, so once again, if we simply have it, forget this term. If it was not there, if our cost function is to minimize this, whatever weights is it picking, isn't it trying to make the actual difference between actual output and the expected output as less as possible, right? Okay, now if the cost function further had lambda w squared, okay, because remember the network is trying to minimize the loss or the cost function, okay? So for it to be smaller and smaller, it has to satisfy both of these, meaning the reconstructed has to be close to the expected, right? But it also has to make this smaller. If this is too big, the cost is high. So it is doing both things, meaning picking small w's that will result in both of these being equal. Does that make sense?
Yeah, okay, so that will take the summation of all the W's existed in the neurons, right?
This is all the w's, regardless, first layer, second layer, last layer, all the w's, this cost loss function will make the magnitude of all the w's as small as it can be so that our goal is satisfied. Okay, so now 2 more minutes that I'll give you a break. Let me at least give you an idea of the dropout. So, okay. Okay, so coming back to reducing overfitting. Okay, we've talked about 2 techniques so far. Okay, the first technique was use validation set so that we do not overtrain. Okay, then the technique I just mentioned over here was weight decay, also called L2 regularization. Okay, the third technique, and by the way, there are a few others as well, but to save time, I'll cover the most important ones. Okay, the very popular one is dropout. Okay, dropout is extremely easy technique. Okay, so keep in mind, it basically zeroes out output of neurons randomly. Okay, but not the last layer. So you never apply dropout to the last layer, okay? Only to the previous layers, okay? So basically, let's say we created a 3-layer network, right? Some weights are connecting here, some weights are connecting here, some weights are, okay. So what we'll do is, each one of these outputs, okay, so this is going over here, this is going over here, right? Okay, so suppose we decide randomly that we'll zero it out. Okay, so if you take a look at our computations work like this, right? Okay, we do sum equal to W of, if it's the first layer plus B, if it's an intermediate layer, then remember it's the
A times A.
previous output, which is the actual output, right? Okay, so from an implementation point of view, all you're doing is randomly setting the A to 0. Not all A's, some A's. Okay, so the question, so in the first epoch, let's say we zeroed out this one, okay, and we still make it learn the same way as before. Second epoch, we pick some other neuron whose output to be zeroed out. So everywhere it goes, it will feed in a 0. So the idea is like this. Whatever we are not zeroing out, it has to pick a value of the weights to compensate for zeroing out, meaning, you know, those weights are learning the proper reconstruction or proper classification. So even if it was an additional neuron that's not needed, it's learning how to skip that but still be able to. So intuitively, it's an extremely simple concept, right? From an implementation point of view, it is also extremely, extremely easy. As I will show you, really 2 lines of code is all you need to implement dropout for regular networks. For deep convolutional networks, it becomes a little more involved. At that time, we can revisit this part. But anyway, for right now, okay, how do we implement it in Python? Very easy. Okay, so in Python, if you create, for example, let's say some array Z, random dot binomial. Okay, then 1 comma p. P is the probability. Okay, and then whatever shape we wanted. Okay, so this is the shape. Okay, so it could be 100 by 1, 10 by 1, or whatever, right? Okay, so for example, let's say we wanted 80% of the neurons to be kept, 20% to be made 0. So then you'll pick P to be 0.8, right? So then what you will do is, see if you now, there's one small issue over here. Okay, let's say, forget dropout, right? At some point in time, this was producing an output of 2, output of 0.1, output of negative, oh sorry, let's make it sigmoid, so it will always be 0, 0.3, and so on, 0.5. So some layer, pretend these are the outputs. Okay, if we take a look at the average value of the output, okay, in the technical terminology, that's called the expectation. What will be in this case? Won't it be 0.2 plus 0.1 plus 0.3 plus 0.5, right?
Yep.
Okay, now let's, because remember we are zeroing out some of the neurons, so let's pretend there were 10 neurons over here. Few of these, suppose this was 0.1, 0.2, so these got zeroed out. So my question is, will our average be still the same?
No, it will
decreases.
It will decrease, right? So basically, to make sure the average result still stays the same, what we do is we divide it by P. So in other words, this, once we create this variable, we divide it by P. So to give you an example, if let's say our shape is 10 by 1, what kind of data will it create? Without dividing by P, it will be something like 0, 1, 0, 0, 0, 1, 0, 0, 1. Oh, sorry, only 2 ones, because I picked 0.8, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So now if I further divide by 0.8, okay, what will it do? It will make this.
1 by 1.
Oh, I did the opposite, my mistake.
It's supposed to be 8, 1.
8 ones and 2 zeros, yeah. So, 1, 0, 0. Oops, let's make it 1, 0, 0, 0, 1, 2, 3.
Just 2 zeros.
Just 2 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so just 2 zeros, right? So without this divide by P, this is how it will be. But as we divide by 0.8, it will become 1.25, 0, 1.25, and so on. Okay, so basically what we'll do is the actual output is being produced, A will become Z times A.
Oh. Will it be in each and every layer after it?
Not the last layer,
Except the last.
except the last layer.
Okay.
Okay, so anyway, from implementation point of view, it's that easy. Create a binomial distribution, divide by the P, so that we can scale it so that the end result expectation is still same as the original data. And then every actual output inside the neuron becomes Z times A. So as you can see, some of the outputs will get zeroed out, some of those will get enhanced. Okay, as we do the back propagation, we have to do the same thing to the gradients. So the gradients also will get multiplied by the Z so that they don't contribute anything as they go back, right? Let me quickly show you the code, then I'll give you a break.
Professor, here we divided by B. It looks like we increases the weight.
We increase because remember we wanted the average of the outputs, because this is getting multiplied by the output, right? This is getting multiplied by the output. Because some of the outputs will get zeroed out. This output will become 0.
Yeah.
right? We don't want to reduce the average, so for us to keep the same average, we enhance
The one.
the ones which are being preserved.
And for every epoch, like, do you always zero out the same ones, or
No.
every epoch you change?
Totally random. Yep. Okay, so I'll give you the code of the implementation as well. So let me quickly show you the code. It's pretty easy, like I said. Okay, so if I take you to the layer class. Okay, so if you can take a look over here, I created a variable
0.
called zero out, which I will put the binomial data in it later, okay, if a dropout is being used. So as I go to the evaluate, okay, so take a look over here. Like I said, we don't apply the dropout to the last layer. So if the last layer is false, then binomial, okay, somebody will give us the dropout, like 0.8 or whatever, right? Okay, then take a look over here. Does this line make sense? Look, right? Because it's the output we are zeroing out. Okay, then this is the derivative of the activation function. You also do the same.
Same thing.
Okay, and anyway, rest of the code, like I said,
Can you show the
is
back propagation? Will that be also be multiplied by the 0 outcome?
this takes care of the back propagation because the derivative is used in the back propagation.
Got it.
Okay, so let's take a break and then we'll continue from here.